All right, let us discuss about introduction to limits. Before we go to limits, let's see this graph as an example and what will be the values of g of x when x is negative 1, 0, 1, and 2. Let's see from the graph. As you can see from the graph, when x is negative 1, let's say this one, x is negative 1, y is negative 1, positive 5, right? It is positive 5 when x is 0. You can see that x is 0, y is 2, this is 2, x is 1, y is negative 1, it is negative 1. When x is 2, y is negative 4. So these are the function values from the graph, reading from the graph. Now, what is the difference between functional values and limit values? So the functional values are the exact value of a function when x is some specific values, but the limit value is what will be the value of the output when you are approaching from the left and the right side without exactly touching the point. That is the definition of limit. For example, let's see also this is a continuous function. There is no gap on the function. There is no hole. Now you can read from the graph, for example, negative 1, negative 2. And when x is negative 2, you can read from the graph it is positive 1. When it is negative 1, it is around 1.5. When it is 0, it is 2. When it is 1, it is 2.5. When it is 2, it is around 3. When it is 3, it is, you can see it is 3.5. When it is 4, it is 4. So these are function values. Now, how can we analyze the limit value? The limit of a function at some domain value of x is equal to a involves examining the behavior of the output values. Here is the point of the function as the input value gets increasingly closer to the domain value of a. For example, let us sketch the graph. In order to sketch the graph, x-intercept means when the value of f of x is equal to 0, so that x plus 2 is equal to 0, which is x is equal to negative 2. That is the x-intercept. The y-intercept is when the input value x is 0. That is f of 0 is equal to 0 plus 2, which is 2. Now, since this is a linear function, 2 points are enough to sketch the graph. Let's draw the graph. Let's say this is a y-axis, this is the x-axis. Let's say the x is negative 2 here. This is positive 2 here. Now connecting the pointers. Connecting the point. Now this graph is y is equal to x plus 2. Now when x is go closer to 2, remember this is, let's say, 2, so what will be the value of y? Now in order to evaluate this, assume that you are getting closer to 2 from the left and getting closer to from the right. What will be this value? It is, substituting 2, and the limit is written as what is your value when you are approaching x from the left side, which is the notation is on the top, negative, of f of x. That is, you have to plug in 2 plus 2, which is 4. Again, when you approaching limit of x approaching 2 from the right side of f of x, the same thing, 2 plus 2, which is 4. And the function value is f of 2, which is exact value, x plus 2. This is 2 plus 2, which is 4. Now, the limit from the left, the limit from the right, and the function value are the same. In this case, we call it the function is continuous at x is equal to 2. Now, there is a formal definition of limit. So the definition states that we write limit of x approaches c of f of x is equal to L, or f of x approaches L as x approaches c if the functional value of f of x is close to the single real number L whenever x is close, but not equal to c. This is an important definition of limit. So the limit value is different from the function values. Now let's see this one. It is similar. You can sketch the graph of this one. Let's sketch this one. The x-intercept is when y is equal to 0, which is -1 here. When x is 0, it is +1. And when you draw the graph passes through these 2 points. So this is a graph of y is equal to x plus 1. Now, what is the behavior when you are approaching from the left and right? Assume that you are approaching from the left side and the right side, very close. So in limit notation, you can just write limit of x approaches 1 from the left side of f of x. This is just substituting 1 plus 1, which is 2. The same limit of x approaches 1 from the right side of f of x. Just substitute 1 plus 1, which is 2. And the function value is f at 1. It is 1 plus 1, which is 2. And 3 of these values are the same. Then we can say that the function is continuous at x is equal to 1, since the 3 values are the same. I'll go to the definition of limit, one-sided limit. That means the limit from the left side and the limit from the right side. Remember, when we say limit of x approaches left side, you have to write a negative on top of the number. That is limit from the left. And on the right, you have to write c plus, which implies that you are approaching the value from the right side. So these are the limit. And this is an important note. If no direction is specified in a limit statement, assume that the limit is two-sided or unrestricted. This is important definition of limit. Now, this is a good example to see the difference between the limit from the left side, from the right side, and the fractional value. Look at now this point. For example, if you look at a limit at x near -1. Now, this is continuous, so just look at this, approaching from the left side, approaching from the right side. Now, when you look at limit of x approaches -1 from the left side of f of x, you can read from the graph, it is 1. Limit of x approaches 1 from the right side of f of x, it is the same, it is 1. Limit of limit of x approaches 1 of f of x is 1, because the left side is the same as the right side. Then you can put without any plus or minus, which is 1. And the fractional value at this is -1, there is -1. -1 is equal to, it is 1. So the function is continuous. Now, the interesting pointers are at -1. Do you see there is a hole? There is a hole. Now, when you're approaching from the left, from the right of 1. Now, we can say limit of x approaches 1 from the left side of f of x. You can see from, you can read from the graph, it is 3. Limit of x approaches 1 from the right side of f of x, again it is 3. And limit of x approaches 1, therefore, of f of x is 3, because the left side is the same as the right side. Now, the important thing is, what is the fractional value at 1? You can see there is a hole. That means exactly at that point, the function is undefined. Do you see now the difference between the limit value and the function value? This is known as function value. These are the left, the right, and the limit. Another interesting point here to analyze is this point. Now let us look at the limit of x approaches 2 from the left side of f of x. The limit of x approaches 2 from the right side of f of x. Then what is the limit x approaches 2 of f of x? Then what is the fractional value at 2? Now from the graph, the left side, when you are coming from the left side, look at, this is the point, which is from the left side, or you can look at, this is the left side, this is the right side of the graph from the point that we are under consideration. So from the left side, you can see that it is 2, right? 2. From the right side top, you can see 5. So this one is, the left side is different from the right side. In that case, you have to say it does not exist. And the fractional value, look at the shaded part. The shaded part defines the fractional value, and the fractional value is 2. So the limit does not exist because the left side is different from the right side, and the fractional value is defined, but it is different from the left and the right side. Remember, the fractional value is defined on a closed or shaded circle. Don't forget this. Now, interesting pointers. Now, let us analyze this graph. Now, it says 0, 1, and 3. So, our point of interest is 0 and at 1 and at 3. Now, if you are asked to analyze the behavior of f of x at x is equal to 0, 1, and 3. So let's do 3 of them. Now, when you look at limit of x approaches 0 from the left side of the function, it is defined. There is no gap, you see. So this is just 0. Limit of x approaches 0 from the right side of f of x, 0. And then you can conclude that the limit does exist at 0 because the left side is the same as the right side, 0. The function value at 0 is also the same. There is no hole, there is nothing. That is. Now, this is at x is equal to 0. Now, the second one, let's analyze x at 1. Now, look at the limit of x approaches 1 from the left side of f of x. When you just look at the y value when you are walking from the left side of 1, you can see this one is, the value is 1, right? From the graph, limit of x approaches 1 from the right side of f of x. Now from the right side, look at the right side, the right side, the right side. This is the right side. Right side, this is the left side. The right side, you will see a point which is 2. Now, limit of x approaches 1 of f of x does not exist because the left side is different from the right side, and limit of now the function value, now function value at 1, it is open on both, it is undefined. So for the function value, we use the word undefined. For the limit value, does not exist. DNA stands for does not exist. Now, the last point is, let's consider x is equal to 3. Now, look at the graph. Limit of x approaches 3 from the left side of f of x is just, you can see, it is 3. Right? And limit of x approaches 3 from the right side of f of x is again 3 at the same point. Then limit of x approaches 3 of the function, since both the left and the right are the same, then 3. However, f at 3 is undefined. So these are. So please make sure that you understand the does not exist for limit and undefined for functional values. So there is a theorem here. It says that for a two-sided limit to exist, the limit from the left side and the limit from the right side must exist and be equal. That is what we discussed on the previous graphs. That is to say, limit of x approaches c of f of x is equal to L if and only if the limit from the left side is equivalent to the limit from the right side. So on the second video, I'll discuss about the properties of limits and you'll look at the next video.